In the last talk, we looked at two completely different genres of structural systems, bearing systems and bending systems. Bearing systems primarily dealing with forces of compression and using materials like brick and concrete and stone that are good in compression. And bending systems looking primarily at forces of bending and materials that are good in bending like wood and steel. And today we're just going to look at the way those play out and how fundamentally, I think it's kind of shocking when you look at these buildings how much the character and the nature of that building is really being formulated by these structural systems. Compressive structures or bearing systems have been around, as we kind of got a sense last time, since ancient times. But it was the Romans, as we mentioned last time, that really made huge advances in bearing systems. They kind of invented the arch and the vault. And in this case, I want us to look at a building where they took that one step further and created the dome. And now we're looking at using compressive structures, but not just trying to make small rooms or passages, but now making enormous, glorious, beautiful spaces while still keeping the materials in compression. And the prime example of that is the Pantheon in Rome, built between 120 and 124 AD. So this is, again, like with the Colosseum, one of the most famous Roman buildings. It has this incredible interior space. So now we've elevated compressive structures to making rooms, and not just rooms in this case, but magnificent rooms. It's a huge space, 120 feet across, like that, but with 20-foot thick walls that are supporting that dome that sits on top of the space right there. And inside, it makes this magnificent, and maybe some of you have been to Rome, and if you've been to Rome, you've certainly been to the Pantheon. It's one of the most spectacular buildings in Rome. And at the top, there is this oculus where there are no loads, and then it slowly begins to accumulate those loads and carry them into the walls and down into the ground through these thick walls with niches carved out of them. And here you can see how it starts thin at the oculus, gets thicker, and carries those loads down into the ground. And where you want to have a little niche opened up there, then you use an arch to carry those loads that have been coming down around and down into the piers on either side of the arch. So everything's in compression. It's working exactly as we talked about in the last talk. But now it's making this magnificent interior space of that dome. And it's made out of, as you can see in this drawing that was done when the skin of the building had deteriorated. And so the skin is off, and you can see the guts, and you can see those relieving arches, and it's made of brick and of stone and of rubble concrete, all of those compressive materials that are making this incredibly beautiful, beautiful structure. Now, that was kind of the peak of the Roman Empire in Rome. At a certain point, Constantine decided he was going to move the capital of the Roman Empire to Constantinople, what's now Istanbul. And he built this structure, which originally was a church, has been now for centuries been a mosque. The minarets were added to make it a mosque, but it originated as a church in the time of the Romans in the later part of the Roman Empire. Now, in this case, it's just taking the Pantheon and going one better, in that the Pantheon started with just that dome, but now we have the dome being supported by semi-domes on either side, and those semi-domes being supported by 3 other semi-domes around here, and then the whole thing carrying those compressive loads slowly down, and into massive piers that take them into the ground. So now we're getting an incredibly impressive structure, mammoth building that again is in compression, is made of stone primarily, and carrying all of those loads from the dome at the top all the way down to these massive piers and making a kind of pyramidal shape out of that. That's just the shape that a compressive structure wants to take. Inside, incredible, impressive, magnificent space. Almost a football field kind of space inside with that massive dome in the center and then the semi-domes on either end extending that and the 3 semi-domes beyond that extending it even further. And you can tell by the scale of the people down here, an incredible, impressive, and massive room. And all the way through Hagia Sophia, you get this explication of compressive structures, those incredible vaults, those groin vaults that vault in 4 different directions, carrying down into those massive compressive walls. And you can see the materials, very explicit in many parts of it, how that brick is now making this incredibly beautiful structure that really becomes, honestly, the character of the building. And in plan, we're seeing how that dome and then the semi-domes beside it and the semi-domes beyond that are now making this huge continuous space all the way through there that you can imagine at the time just blew people away. This was like a moonshot. It was like accomplishing something magnificent and amazing people hadn't seen before. But it was really the advances of structural knowledge and taking compressive structures just as far as they could. And then every detail of it, the shape of these windows are really that arch shape and making as slender an opening in that dome as possible, but carrying those loads around it and down into it. The big dome going into a squinch here that then allows them to have the semi-dome on the other side. All of those beautiful, graceful forms that we look at and say, wow, they're amazing, they're beautiful, but they're just structure. They're really doing exactly what makes a compressive structure work well. And it enables then this magnificent, huge indoor space that was an emblem of the Christian religion and of Rome's power and capability way back in the 3rd and 4th century AD. So over and over, we can see in those magnificent buildings like the Pantheon and Hagia Sophia, the expression of structure really making these incredible buildings. But even in much more modest instances, this is a gatehouse for a large estate in northeastern Massachusetts. The architect is H.H. Richardson. We've looked at Richardson's work a bit before. We're going to continue to look at Richardson's work through the class. He was probably the best known American architect of the 19th century. And here he's making a normal kind of house, but he's making it out of stone, out of a compressive material. And the architectural expression is taking that notion of, yeah, it's stone. I could just lay it up in an ordinary way. Or I could really kind of give a sense of, what is that stone? What is compression? How does that feel? How could I, in some ways, kind of exaggerate it to make a really powerful character of this building? And that's what's happening. He's making those stones, which are local Roxbury pudding stones, these kind of bulbous stones, feel like they've got the weight smashing them down and pooching them out from the side of the building. And when he opens up an arch here, he expresses that keystone in the arch and the voussoirs very prominently. And you get a feeling of how forces are moving through that building and how those forces are now making incredible architectural form. Sometimes he doesn't use an arch. If he uses a stone piece to span, he lets you know, I've got to use a big ass, huge stone. I've got to corbel out to make that span as small as I can make it. But everywhere through the building, although it's not heroic dimensions of compressive loads, he's expressing the compressive loads in a pretty powerful and wonderful way. And the one place where there is a bigger dimension is at the actual place where the carriages would go through. It was a gatehouse to this estate. And at that moment, he does open up a big arch there. And at that point, it gets to be a little more dressed stone. And you get the sense of this big, powerful structure enabling that opening to occur in the building. So this is structure as inspiration for architectural expression in the case of the Ames Gate Lodge. Just to make the point that this is something that happens in older buildings, ancient buildings, 19th century buildings, but this is also something that has relevance in 20th century and 21st century buildings too. This is a dormitory by Eero Saarinen. Again, Saarinen, someone we have looked at before, we'll continue to look at through the whole class. Very prominent architect in the middle of the 20th century. Here he's building 2 dormitories at Yale University, and he's building them in a part of the campus that has a lot of older masonry structures. So the graduate school here is a neo-Gothic structure with very tall masonry piers that are making that neo-Gothic shape. And he takes really those forms. This is another building adjacent. This is the gymnasium, which again is a neo-Gothic building with strong masonry piers. And he takes those cues and says, well, as a contextual response, I want to make this feel like a masonry building and feel like that kind of powerful structure that you see in neo-Gothic buildings. So he's making a modern building, but he's using that masonry. In this case, it's a very interesting kind of concrete. Normally you make concrete out of cement and large aggregate, which is usually stones about 1 inch or 2 in diameter, and small aggregate, which is sand. In this case, he's making the large aggregate much larger. So he's actually using stones that are 6 or 8 inches. And still structurally they behave the same as the concrete. But he's exposing them a little bit on the outside of the building so that you get this nice texture and color and shape of the material. But he's making a good compressive material, this concrete material that he's using in compression there. And he's using it in the sensible way, just like you can see in those piers of the neo-Gothic buildings. And then he's making very small spans because, and there he's using reinforced concrete where he puts a little steel in there and that enables it to act in bending. But he then makes the masonry compressive walls here and then the smaller spans with their windows, but making really very, very narrow openings, really similar to what you saw in that neo-Gothic building there. So the character of this building, again, very much shaped and formed by the structure and the materials and fits beautifully into that part of the campus as a modern building, but behaving structurally and using similar materials to the historic buildings that were around it. Okay, that's one whole genre, is this notion of bearing structures, compressive loads, materials that respond well to compressive loads. Let's look for a minute at more bending structures. And this is a completely different thing. We're gonna look at Japan in this case because Japan was a country that had tons and tons of forest. The whole archipelago of Japan is mountains covered with forest. So from ancient times, they used wood as a building material. And they learned that when they use wood as a building material, it's very good in bending, so you can make very good bending structures. In the 15th century, we see them making all of these separate little fiefdoms with their rulers or daimyo. Would want to make a castle that was the biggest badass castle around. And there was a kind of competition among these warlords in different areas to build the biggest and coolest and grandest castle. So in this case, we're seeing one of those castles. This is actually the structural system within that castle. It's made of big timbers, huge, massive timbers that are making that shape. And it enables all of these cantilevers that are all in bending, and that whole character of that Japanese building being lighter and kind of defiant of gravity, not so massive and tied to the ground. There's some of that at the bottom, but as you get up in the structure, it's really reveling in the fact that it's a frame and that it's in bending. This is what that looks like on the inside, these massive timbers, columns, and all of them are, when you put a load on a column, it wants to bend. It wants to have tension on one side, compression on the other. When you load up a beam, it wants to bend, sag like that, and have tension on the bottom and compression on the top. So all of these are in bending, and they're using the wood, which is a great material for resisting that bending. This is the largest wood structure in the world, has been for centuries. It's Todaiji, a temple in Nara in Japan. This is, you can see by the scale of the people right here, massive, massive building with these deep cantilevers and overhangs in bending. The columns here are like tree trunks, like redwood tree trunks, huge beams that go across like that, and then cantilevers and supports. The whole architecture is about how do you resist these bending loads? How do you make a frame out of all of these bending members? And then you can get expressions like the pagoda, where it's a very slender support in the center, but then all of these cantilevers that are in bending give that light, delicate quality they were after in Japan that created something as delicate as the pagoda. But as you go through all of their buildings, it's all about expressing the structure. The trusses down here, the beam up here, the support for the beam, the intersections of where a beam hits the wall, and the transition of that load into the wall. All of the character of the architecture is based on structure. Now, there were centuries of them building in Japan with these massive heavy timbers. And because they had kind of endless forest, that seemed fine. And they built all their cities out of wood. And occasionally there'd be a fire that would come through, and of course wood burns and it could be very destructive. That was fine. They'd just come back and harvest some more forest and rebuild the city. And that happened for centuries in Japan. And then in the Tokugawa era, there was a period of great affluence. The culture was booming, the economy was booming, population was growing, the cities were growing. And in Edo, which was the capital, now Tokyo, there was a massive fire. And there was huge destruction. And that wasn't the first fire they'd had in Edo. It had happened before. So they went to rebuild the city, and they went up to the forest and realized, oh my gosh, we're running out of wood. So the resource began to be limited, constrained. And they began to think, well, we've got to maybe respond to that. How can we build with wood, but maybe in a more economical way? Not use so much wood, use it in a more sparing way. So they continued to build in wood, but they changed the way they built in wood. And in a way, this is a wonderful example of sustainability, where at a certain point they realized they had limited resources. They had lots of forest, but they were going to have to farm those resources, and they started elaborate silviculture there. And then the steeply sloped areas were reserved for forest. The shallower slopes were reserved for their crops. And then they made very concentrated villages in small areas so as not to compete with the forest, not to overwhelm the forest. They needed that forest for the wood that it provided. And this is the little village of Tsumago, which is all made out of wood. And it's very interesting just to see every single house, every structure there is very, very explicitly in wood. And now they're beginning to have that notion of how can we use the wood in a very efficient way? And they start to really express that frame of the columns and the beams. And they make infill material that is not quite as massive or as, it's not using as much resource. So now we get the wood only really where it's playing the structural role there. And then maybe just very thin infill between there. Inside, they're opening it up because now with a frame system, you don't have to have the big thick walls. You can have much larger spaces where you're spanning over. They begin to make partitions not out of all wood, but out of shoji screen, which is actually wood made into paper, but now much more lightweight, much more flexible, movable, and at the same time, quite beautiful. So it's really the wood and the structure and the resource that is now shaping the character of the interior. They begin to realize that now with this frame, we can have a lot more connection between the indoors and outdoors. Very different from a compressive structure, a bearing structure, where you've got to have that structure to support the building. And it means the penetrations are fairly infrequent. But in this case, we've got the frame. You can open up the exterior, get a lot more light and air and view. You can begin to get connections to the gardens. They begin to make much more elaborate gardens and have the activities of the house spill into the garden. So every aspect, even the functional aspects of the building, are being affected by the structural system and by the use of that frame and the flexibility of that frame to do things that they discovered once they had the limited resource. They can make less and less and less of that wood. They can make less and less solid walls. And now they're beginning to really make much more connection with nature and the outdoors. Now, that's a demonstration of how wood has been a fantastic structural material, inspiring architecture, definitely in Japan, but all over the world as well. The same thing could be said of steel. We've looked before at Mies van der Rohe from the very early talks in the class. Mies van der Rohe was, as I mentioned, in terms of his values, very connected to construction. Construction was important to him. And in most of his buildings, we're seeing a very explicit expression of the structure. This is the Lakeshore Drive Apartments, these two buildings in Chicago. This is them under construction. You can see this just simple, elegant steel frame, square bays, kind of minimum amount of material to get the maximum benefit structurally. And just the two buildings right here, the two towers. It really is allowing now, because of the frame, gorgeous views out to Lake Michigan, gorgeous views back to the city. I have some friends who have a place there right now. All these years after it was built, it's still a spectacular building to live in. There are those two buildings right on Lake Michigan there. It also allowed the floor plan to open up so you get big interlocking rooms, openness between the living room and the kitchen, and all of that opening into easy open interior spaces, and ones that in a compressive structure, bearing structure, would be impossible to have. But it's both opening up the interior and also allowing these spectacular views. This is actually how two pieces of steel go together in Lakeshore Drive Apartments. They have to be reinforced, and there'd be rivets and bolts and things like that to transfer those loads through the frame. But Mies van der Rohe, he expresses the nature of the frame without literally showing you all the behind the scenes work, so that you get this expression of steel I-beams on the exterior of the building, which actually are carrying some of those lateral loads. But then basically the frame of the building being prominent and very much revealed at the bottom of the building, where you get the sense of exactly what the structure is. And then all of that floor to ceiling glass and ability to open up and get the connectivity on the ground floor to the gardens around and the view of the Lake Michigan beyond. But on the upper floors, spectacular, spectacular views in the building. So part of what we value these days in downtown condos with spectacular views of the sky and of the city, that's enabled by the frame. That's enabled by the fact that there's a structural system there that's able to give that opportunity. Maybe the very most complete frame building or structural system expressed as the architecture of a building is the John Deere headquarters in Moline, Illinois. And this one is done by Eero Saarinen. We saw Saarinen's Morrison Stiles College a minute ago. The same architect, same period of time. In this case, he's doing a spectacular office building for John Deere, which is a company that manufactures farm equipment. So they make mechanical kinds of things, steel structures for farming. And the building takes on very much that kind of character. It's all very explicit in its girders and its beams and its purlins and its columns, and all of those structural pieces are put together with passing connections. So you almost see the building being constructed like Tinker Toys. You can see its explicit structural assembly very clearly in the architecture of the building. It's also made out of what's called Corten steel, which is the steel where the steel rusts, and you don't have to paint it because the rust forms a coating on the outside of the steel and prevents it from rusting any further. And so you get this natural color of the steel set in this very, very natural environment, hundreds of acres of woodlands. And you get, again, those beautiful views out to the woods from the structure inside, and this openness that the frame provides. So you can get massive, huge, open areas so they can display their farm machinery. Even in the office spaces where the spans are not so large, you get these incredible views out to the natural environment beyond. It's really the whole architecture, the character of the building is rooted in that very explicit, very sensible frame structural system. Now, at the close here, I want to make a similar point to what I made several talks ago. When we were looking at the work of Frank Lloyd Wright, we looked at Falling Water and Taliesin West in the same lecture. And those two buildings are incredibly different from each other, even though they were built and designed at the same time. And I was making the argument that this notion that a great architect has their style they work within is baloney. In that case, you have a really great architect. He's not just sort of trotting out his style. He's responding very sincerely to the differences of this site and this landscape and that site and that landscape, and it's making completely different kinds of architecture. I would say the same thing is true here in these two buildings we looked at in this talk, both by Eero Saarinen, both done at exactly the same time. This one at Yale, where he's taking a cue from the existing buildings and using masonry and making a compressive structural system there. And that generates one kind of architecture. And at the same time, on a completely different site and for a different client, where he's interested in getting big views out to nature, long spans, a kind of technical metal quality that John Deere incorporates in their machinery as well. Now he's working in steel, and he gets a completely different expression there. The bottom line here is Eero Saarinen's not doing the Eero Saarinen style. Eero Saarinen is making great architecture by understanding, in this instance, I'm working with this structural material and system. In this instance, a completely different one. And that's going to make very different, equally sophisticated architecture in both cases, but it is the structure and the materials that are leading the direction of that design. Okay, see you next time.